How long does Earth take to rotate on its axis?
From what I've been told, 24 hours.
24 hours. Okay. So as you might have guessed, it doesn't take 24 hours. It actually takes 23 hours, 56 minutes, and 4 seconds. Okay?
Really?
Yes.
Now, wait a minute.
Wait, hold on. So let me just be clear about what I mean.
23 hours.
Get rid of just get rid of the entire solar system and watch Earth rotate. Okay? And stand there and time it. That spot that's in front of you will come back around in 23 hours, 56 minutes, and 4 seconds.
One full revolution. Okay.
Yes. Okay.
Gotcha.
That's called a sidereal day.
I like
sidereal
this.
means star day. So you're measuring with respect to the universe. However, we don't base our lives on when stars return to the same spot in the sky, in the night sky. We base our days on when the sun returns to its spot on the sky. Okay? It turns out that takes longer than 23 hours and 50. Why? I'll tell you why. Because in the time it took Earth to rotate 23 hours and 56 minutes, it actually moved almost 1 degree in its orbit around the sun. Gotcha. So it rotates back to where its previous line, but it has to turn a little bit extra.
A little bit extra to get back to the same.
Little bit extra to put the sun back in the same spot on the sky.
Right.
And that's 4 minutes extra.
That's fantastic.
And why did I say?
Oh my God, that's just. I love that.
I've only just begun. So that little extra 4 minutes. So I said we move a degree in our orbit each day. Right. I didn't just pull that out. How many days are there in a year?
365.
Okay, and how many degrees in a circle?
360.
Yeah, so it's about a degree a day.
It's about a degree a day.
And in that degree, you have to turn that little extra. So just imagine you keep having to turn your head.
Just a little bit
extra
more.
amount. Okay.
Because you move just a little bit, so now you got to look back just a little bit.
Correct.
That's cool.
Well, let's keep going, okay?
All right.
Earth's orbit around the sun is not a perfect circle.
Right.
Which means sometimes we're farther away, sometimes we're closer. When we are closer, we are moving faster in our orbit than when we are farther away. So it turns out that extra 4 minutes is not the same if we're farther from the sun than if we're closer to the sun, because we moved more than our allocated fraction of a circle when we're close to the sun and less when we're farther away from the sun.
Gotcha.
Okay. So the length of the solar day is changing continually throughout the year.
Wow.
And sometimes it's less than 24 hours. Sometimes it's more than 24 hours. So sometimes the sun gets to its highest point in the sky before clock noon.
Right.
And sometimes it gets, so what we do is we just average that over the whole year and say, sun, you are average 24 hours, and there you go.
Wow.
By the way, if you ever look at sundials, there's a map on the sundial that corrects for the sun being early and the sun being late. You either add or subtract up to 14 minutes of the day from what the sun time reads in order to get your clock time.
Wow.
All right. Every sundial has it. So it's a figure 8. It's called an analemma. It's got a name, an analemma. But I don't want to talk about analemmas right now. So what you have on your clock is the average length of a day over the 365 days of the year. All right. So now we define that as 24 hours, each hour 60 minutes, each minute 60 seconds. Got it. Okay. Well, what is defining this? Well, it's the rotation of the Earth.
Right.
Okay.
Makes sense.
Well, all right. Well, how stable is that? Even in the perfect average that we're taking. Well, you'll never know, will you? Because you're using Earth to define the time frame.
Right, exactly.
Okay? If Earth is your measure and you are slowing down, you will never know this. So now, you pose the question, maybe Earth is not the best timekeeping device. Let's offload the responsibility of keeping time to something else, like a vibrating atom. So we did that.
That sounds
cesium, so the cesium-137, there's a electron transition between two energy levels that has a very precise frequency. Okay? Very precise. You can measure. What's good about that is any lab can get some cesium and measure this and then define the length of a second in their lab. Okay?
Okay.
When you do this, you multiply it by 60. You multiply that by 60, you get the hour. You multiply that by 24. You do this and you find out that Earth is slowing down.
Well, it's kind of old. I'm just saying.
It's been added. It's tired.
It's a long time.
It's a tired Earth.
If you're 4.6 billion years old, you might slow down a little bit too.
You might be tired
I'm
too.
just saying, you might lose a step on your game.
Okay, that's very sweet of you, Chuck. That's very geriatrically sensitive of you. So you only would know that Earth was slowing down once you offload it to something else that tracks time.
Right.
And what we found out is that the sloshing of tides on the ocean floor, on the beach fronts, actually works to slow down the rotation of the Earth.
Oh, wow.
Okay, because the moon is causing these tides.
Right.
Okay. And we're rotating faster than the moon is orbiting us. So the moon is tugging on tides backwards on our attempt to rotate.
Right.
Okay?
So it's almost like there's a counterweight.
A counterbalance, exactly.
Yeah, counterbalance that's pulling against what?
Against us.
Wow.
So tides are slowing down the rotation of the Earth. And in response, the moon is spiraling away from us by a couple inches a year. Okay? That's in response to Earth slowing down. It all relates to what's called the conservation of angular momentum, but it's a big ballet. Okay? Mm-hmm. And so we've been slowing down. And Chuck, what we could do is say, let's redefine the second, the length of the second, so that we always have 24 hours and 60 minutes and 60 seconds. But that's messy. Right. If every year, here's a new definition of the second, folks. Go to your lab, redefine the cesium atom. So the way we compensate for this is
how?
We add a leap second.
When do we? Oh, well, it has to be every 4 years. Then we add a.
No. Did I mention years at all? I'm talking about days, dude. Days.
Every 4 days?
No. What I'm saying is we monitor when we have fell behind by a second.
Okay. So when we know that we've lost a second based on our atomic measurement.
Correct. Then internationally, we say time to throw in a leap second.
Now we throw it in.
By convention, we throw it in on June 30th or on December 31st. And we can throw in one at each time if we needed it, okay? Right. Since 1973 or 4, something like early 70s, there's been 24 leap seconds added to the calendar.
Sweet.
So when they're going to add a leap second, they choose which of those days it will be. When they do so, that final minute has 61 seconds in it.
Nice!
Yes, it's very cool. It's very cool. Other things that can change the rotation of the Earth, not just the tidal sloshing.
Right.
Okay, but here's one for you. You ready? If Earth has an earthquake and one of the continental slabs shifts north, okay, then there's mass on Earth's surface that used to be closer to the equator the day before and has now moved closer to the pole. That will have the effect of speeding up the rotation of the Earth.
Right.
Large animals that migrate, okay, will change where the mass of the Earth is from the northern climes down to the south, and they're farther away from the rotation of the axis. So not only do tides affect the rotation of the Earth, seasonal migration of animals affects the rotation of the Earth, and so does earthquakes, so do volcanoes, and anything else that's remapping the surface of the Earth. And you know what else will change it? The melting of land glaciers.
Uh-oh, we're in trouble.
Okay, you got Antarctica has land glaciers as it melts. What used to be right there near the pole now melts and goes closer to the equator. That will slow down the rotation of the Earth. So all of these factors combined, basically, Earth's day has been increasing rather than, in principle, it could decrease depending on what's going on.
Right.
So I'm just saying the rotation rate of the Earth is susceptible to all these small effects that can add up. And we deal with it. We throw in leap seconds.
23 hours, 56 minutes, and 4 seconds.
That's our rotation rate to the stars.
To the stars,
It's exactly 24 hours on average, and that average is changing.
Right. Oh man, that's so cool, man.
So that's all I got to say. I mean, it's a fascinating thing.
That is fascinating.
And I love thinking about it just because of how many different branches of the science and technological world had to come together to figure this out.